So this lecture is about audio and audio compression and coding. Strictly speaking, compression and coding are different, although we've been using them interchangeably. Compression is compression, reducing the size of audio data. Audio coding is changing it from one format to another. So I could change my audio from one format to another, and in the process I can compress, or in the process there's no compression. In fact, in some cases there may be expansion. Okay, so we may use coding to refer to compression, but strictly speaking, the two are different. Now, before we begin, it is essential for us to know how exactly an audio file, how the size of an audio file is determined. Okay, there are four major factors that affect the size of an audio file. The first one is the sampling frequency, F. The sampling frequency, I'm sure you've done a great deal of this in digital signal processing. I hope you did. The second is the number of sampling channels. When we are sampling through an analog to digital converter, we have 4-bit, okay, so we may have a 4-channel ADC, meaning that ADC can measure 4 different signals at the same time. We may have an 8-channel ADC, we may have a 10-channel ADC, etc, etc. Now, usually, for sound, we have either 1 channel, that's what we call a mono-channel recording, or 2 channels, that is what we call stereo audio, or 4 channels, that is what we call quad-channel audio. Then we also have the number of bits per channel. Well, usually, if we say an ADC is a 16-bit ADC, that means all channels on the ADC are going to measure in 16 bits. But it could be different. Hypothetically speaking, it could be different. You could choose to measure 16 bits on one channel and 8 bits on another channel. Okay, so the number of bits per in audio, in ADCs for sound, for example, the sound cards of your laptops and personal computers, usually we have either 8 bits or 16 bits. Commonly these days it's 16 bits. Okay, and we have 2 channels. And well, you know, the difference between an 8-bit ADC and the 16-bit ADC is that one is more accurate than the other. So if you want studio sound, for example, in these high-end recording instruments in the studios that most of these musicians use, sometimes they even go up to 24 bits, okay, per channel, because they want to record every tiny bit of information. That is usually what differentiates a great deal. The sampling frequency and the bits per channel is usually what differentiates a great deal between normal recordings that you do on your phones and also the recordings that are done in studio by performing artists. And of course, the sampling duration also matters. Now, you multiply all these. Each of these 4 parameters has a unit. Multiply the units and find out what the units of the resultant answer are. This is an example. An audio, supposing we have a 3 minutes long audio sample and we are sampling at 22.05 kilohertz. 22.05 kilohertz is a standard frequency, a standard CD audio quality frequency. And we are sampling from 2 channels on an ADC whose resolution is 10 bits. What is the size of the audio file in megabytes? Everyone has to do this number. Now, when we are compressing audio data, there are 2 main principles that we look at. One is we can remove redundant information, and 2, we can remove irrelevant information. Okay, these 2 things are different. Well, redundant information, strictly speaking, we can call it irrelevant, but we intend to differentiate between the 2. What is redundant information? This is non-zero mutual information between successive samples of the signal, and usually happens because we have oversampled. Okay, that means we're sampling the same signal value more than once. For example, if your voice has a maximum frequency of 4 kilohertz, so that means if we sample it at 100 kilohertz, we will produce redundant information. What does this mean? We can reduce it to a smaller. Okay, in this case, for example, if you have a signal which is changing at 4 kilohertz. That means in 1 second, it changes 4,000. We have 4,000 samples. Now, if you're sampling it at 100 kilohertz, that means in 1 second you're sampling it 25 times its highest frequency. That means every sample in that signal is going to be sampled 25 times. Okay, so 4,000 samples in 1 second. If you sample them 25, if you sample each sample 25 times, you end up with 100,000 samples in 1 second, and that is what sampling at 100,000 kilohertz will give you. Okay, so when we have a very high sampling frequency and we have a slowly changing signal, we get redundant information. Some data samples are going to be, some data points are going to be sampled faster than they are changing. That means they're going to be sampled more than once, and hence we shall have redundant information. If we remove it, we can reduce the size of the file, and yet we retain the actual data. Then there is what we call irrelevant information. Irrelevant information is unique. It is not redundant. It is unique. However, it is unnecessary. We've seen this when we had a discussion about MP3. Okay, in this case, irrelevant means it is perceptually insignificant. In other words, because of the physiological conditions of the human being, we can't hear it. It is not relevant to us. Maybe it was a low amplitude data point which followed a high amplitude data point, therefore we can't hear it, or it is a series of data points whose frequency is so high that it is beyond that can be perceived by normal human beings. So this is the difference between redundant and irrelevant information. For us to perform audio compression, we have to implement either one of these or even both. So redundancy removal is lossless. I'm sure you can convince yourselves that this is actually the case. Okay, we are removing redundant information. That means we're technically not losing any data. However, irrelevant data is lossy. Okay, that means that we actually do lose some quality of the signal. Okay, most of these processing algorithms are not very exact, by the way. So for example, if you're going to remove the high frequency components, sometimes you end up touching just a little bit of the actual audible frequencies. For if say by saying lossy, we are strictly not looking at it in human terms but in computing terms. If a rat could hear some of those frequencies after performing lossy compression, the rat will not be able to hear some of those frequencies. Okay, so removing irrelevant data is lossy. Now, redundancy removal can be done in a number of ways. Remember, we have n samples that are similar, so we can either skip them, we just take every n samples, we just pick one, or every n samples we just average. That is one way we can reduce the size of the file using by removing redundancy. Now, why do we need to compress audio data? There are two main reasons. The first one is storage. Okay, well, these days storage is cheap, but strictly speaking, we need to be able to we want to fit as many files as possible on a fixed resource. The second is also related to the first, but in this case, the storage is not in one place. We are looking at bandwidth. Okay, the communication channel has limitations. Each and every communication channel has a maximum bandwidth. There is a maximum amount of data that we can transmit through it. So if, let's say, at any one point we can transmit 1 megabyte per second, then recording an audio file that is larger than 1 megabyte per second is going to cause a loss of integrity in the communication. We are going to have higher rates, or we may not be able to pass through 2 megabytes in 1 second, simply because we use the different, maybe because we use the WAV. If we reduce it to MP3, then we may be able to transmit much more information. So those two are the standard reasons why we need to compress audio data, or in general, why we need to compress data at all. Well, there are very many audio coding standards, and perhaps we should first identify characteristics of a good standard before we look at them. Okay, this is just in case one of you perhaps ever gets to want to release your own standard, not only in audio but in something else. Okay, first and foremost, the standard must achieve the desired outcome. Okay, and in most cases this is usually compression. It must allow efficient implementation. Okay, efficient in terms of very many things. One of them is computing resources. Okay, it shouldn't take us 100 seconds to convert a 1 megabyte file. Okay, that should just be a few seconds. So the algorithm that used should allow for efficient implementation. It should be supported by the industry. So really, this is something that comes after the fact. Okay, if there are very many standards that have totally failed to be supported by industry. Okay, so if after implementing your standard, if the industry refuses it, then it is not a good standard. Okay, industry usually adopts what they think are good standards. It should be good for the end users. This is a very subjective term, but a good example of being good is, for example, being cheap. Okay, we shouldn't have to spend a lot of money or any money at all purchasing decoders for the standard that you've implemented. And finally, this is something you could look into. A good standard perhaps should be open source so that it can allow the community to make it better. This is just a small overview of various audio coding standards that have come since the late 1980s. So that's when the ISO, what is ISO in full? That is an assignment, okay? They have an MPEG group, and it started to standardize TV and audio broadcasting, and also the storage of audio on CD. And for audio and video broadcasting, they chose to use MP2. Okay, they developed MPEG 1 layer 2, and for storage on PCs and for internet applications, they decided to use MP3. That is MPEG 2 audio layer 3, or MPEG 1 audio layer 3, because the distinction between 1 and 2 in terms of audio was not as big as it was in terms of video. So this is really just an overview of MP3. We have already had a very standard presentation in MP3 by one of your groups, so I'm not saying much here. You can proceed to read through. So we shall skip this slide. These are the successors of MP3. We have Advanced Audio Coding, AAC. It's now part of the MPEG-4 standard. We have Windows Media Audio, which is the default format for Windows. But all of these really, when they're compressing audio data, they use the same concept, okay? Perceptual coding, okay? They take advantage of biological restrictions of human beings. Speech coding is really audio coding, but specifically for speech. We mainly use it in telecommunications because most of the data that is carried out in telecommunications channels is speech, okay? So it is the process of obtaining small representations of voice signals for efficient transmission over bandwidth limited channels or storage. Well, a speech encoder or a speech coder really converts digitized speech signal into a coded representation, which is usually transmitted in frames, okay? For example, linear predictive coding, okay? Where we isolate the formants and the residue and we transmit them separately. The decoder it does the reverse. It receives frames which are coded and tries to reconstruct the speech. We may lose, depending on the implementation, we may lose some data in the process. Okay, but often speech encoders and decoders are for one particular coding scheme. For example, linear predictive coding, we can have a coder and a decoder. Okay, so we cannot use the decoder of one scheme to decode information that has been coded using an encoder in another compression scheme. Okay. Speech coders usually differ in the bit rate, how many bits per sample or how many bits per second can be coded. Complexity, how many operations per second do we need to code? Okay, some of you, if you're ever compressing digital, if you're ever compressing audio, you see the application telling you running through a first pass filter, running through a second pass filter. These are the operations that we are speaking about. Okay. Delay, what is the amount of time that that is elapses between recording and playback? Okay. And then the perceptual quality of the synthesized speech. Okay. Is it a good representation of what we had originally? So we have narrowband coders. These ones, they code speech signals whose bandwidth is less than 4 kilohertz. And then we have wideband coders which code in the 7 kilohertz bandwidth range. Okay. Now, the Lpc algorithm is the most important speech coding algorithm, and we have previously seen we have previously had someone discuss linear predictive coding. Okay, there's also a very nice video lecture on YouTube about linear predictive coding. For examination purposes, we may focus on the definitions and the applications, but the actual method of how it is achieved and inverse filtering and residues, we may not cover that. Thank you.